last night was interesting. We did the classic extend the opcode computer. So we'll see how complicated of a thing we get tonight. Who knows what to expect. All right, here we go. We're doing orbital fun. Okay. Let's orbits around exactly one object. Around a the A orbits a indirectly orbit. Got it. We had one exactly like this last year. Direct and indirect orbit. Recent build. Okay. Strings. So it's the distance from each node all the way to the top. Okay. Pairs. Okay. Left is the center of mass. Oh yeah, return value missing. Okay. Plus. Not a. Alright, I forget the syntax for this now. I'm. uh. Crash. Correct. Goes 6. Alright, that one's very hot, but we'll take it. Okay. Volume so it's 2 less than the direct map. Objects they are orbiting. Okay. Basically, I just need to go. Parent. They're not the same. Just move. Effectively, I'm just going to move them both up until they meet. Count. Up. And is up. Actually, dribble. Right out. Count. Is correct. 16. Nice. I was hopeful that this was a pretty efficient approach to the second half. All right, so we are 7 minutes in, and yeah, nice. Okay, so now to talk a little bit of explanation. So part 1, basically what I did here was I actually started out tracking children because I thought we were going to need to go both directions. Jump in, do this again. So from this, I actually kind of figured I was going to have to be able to traverse both directions at some point here. But for the purposes of this, all I really need to know is, because I want to know the number of direct and indirect orbits. So for example, D example. So I've got a direct orbit on C and then indirect around B in the center of mass. So effectively, I just have to go count from wherever I am to top. So I just have to count. So for D, it's, at D gets the same count that is 1 plus whatever its parent gets, and so on. D gets 1, 2, 3, 4, J is 5, K is 6, L is 7. Just add all those up. So then that's what this count thing here does. Then by just summing up all of those, I get the totals. Now, center of mass will technically get calculated here, but since the parent is null, center of mass gets 0, so it doesn't end up. Go. Now with part 2, a little more interesting. The way they do it is, as they describe it, they go up. They basically lead you towards it. The problem is knowing what the right path to take here could be tricky if you're just going directly there. However, I take advantage of the fact that effectively the trick is you've got to find their nearest common ancestor and then work out how far away each of them are from that common ancestor. So the easy that is start out. Now I nodes U and nodes San. What? Oh, Santa. Like, this shows you how little I actually read the problem while I'm trying to solve it. Like, I almost feel like I should go back and read the stories after I'm done, because the stories are pretty clever, but I tend to skip over them when I'm trying to get them done as quick as I can. But yeah, so we effectively use not where we start. We start with use parents, with cases K and I. Um, and where the most important part is we need to find this common answer. Well, if we just since we have the count from the previous one, it's easy for us to tell which of them is further down the tree. So whichever one is further down the tree, in this case, it would be point of this. Hey, we just up a level and increment our count. And then, well, this one's still further down the tree, so then we go up to E, increment our count. Now they're both the same distance on the tree, both a 1, 2, both got a count of 4. So we really could move either one of them up. It doesn't matter which one. So I think I'm doing again. So up to D. And now our count is 3. Then 3 moves. 1. And now when we come through the now Sand's count is great. Sand is still pointing at I, so we stand up to its increment our count. Now our count's 4. Now our while loop condition are U and Sand pointing at the same node, and now they are. So effectively reached our termination point, because now we figured out that, well, if I were to take 1, 2, 3 up, and Santa was to 1 up, for a total of 4 moves total, we would be there. Now, our actual goal is to figure out how to get from you to Santa. So instead of Santa moving that last one, it's actually we down to that. But it's the same thing. We're just now, if this was took it to the true actual orbital transfer thing, let's see, subway. So, do we have this as still? Oh yeah, yeah, right. Not called a subway map. It's called Delta V. So there are these cool. Well, okay, I guess this. Here we go. This is one of the nice ones. What I actually thought we were going to do is we were going to get weights for these. We're going to have to figure out what was the most efficient way, or what was the cost of not. Um, so wow, that's not very. Looks like it's transparent, designed to be on white, but actually on black. Anyway, okay, I guess it's here. So this actually okay. This is for the actual realistic solar system. I only search for KSP Kerbal Space Program because that's where I know stuff from. But anyway, these kind of maps demonstrate. So now this case is not obviously in our examples we're center of mass of the sun in our case, but this one's centered on Earth because that's where we start from. But the basic idea is it keeps track of. It tells you like okay, so to get off of Earth we need 9,400 meters a second to get to Earth orbit. To get to an interplanetary orbit, they need another 3210. Then to get to Jupiter, you need 3360. To actually capture into orbit, you need 16200. And then to actually get down onto Jupiter and then get crushed by the pressure, you need 45,000. Now, both these actually have little arrows because you can arrow brake there, but that's not really relevant. In fact, it doesn't have anything to do with anything for this program other than that it has to do with orbital mechanics, and that's what our problem set. Anyway, this is what happens at 11 o'clock at night when I have a little bit of free time and a microphone in front of me. I talk about random things. Anyway, I'm interested to see what solutions look like. Talking with some coworkers today, and there seemed to be some consternation about last night's because it's pretty much just a straight simulation problem. In fact, one guy mentioned the only thing he liked was the opcode decoding. I'm interested to see what clever tricks people come up with to here. I think I stumbled a little bit too much over some of the mechanics on the part, and that'll trip you up in 5 minutes. Times and actually, given this problem, that's actually not that fast. I was on at 5:30, so if I wouldn't have stumbled around quite as much here, I could have been in the mid fours. But I did do very nicely on the second round, and that was because I already had my data structure basically set up the right way. All I had to do was write this, find my things, and work my way up, and understand the problem I was being. Um, actually, yeah, because I was at 5:38. There were only 2 people who got day two before, or who got star two before I got star one, which is not bad. It's usually a bit higher. I was pretty close to the beginning for part two. Anyway, I guess that's been tonight. We'll see what tomorrow looks like. Now tomorrow is going into Saturday, so I think we tend to have slightly harder problems on the week. See if our one of our first weekend days, because obviously the first one doesn't count hard because it's the day one that it needs to be easy, kind of into the flow, and it's also the first problem people try. So day 7, we're going into our first weekend. We'll probably see a little bit more challenging problem tomorrow. Um, but yeah, I'll be interested to see different ways people approach this, because I have a feeling there's some clever trick that involves not having to pass through the thing quite so many times to build things together. You may not even have to build cross-link and just do direct indexing off the data. But we'll see. Actually, yeah, leaderboard's locked. The Reddit thread should be open by now. I'll have to go browse through there, try to approach it. But anyway, that's it for day 6. Back for day 7.